When we have a group of compounds, such as the hydrocarbons, that are consisting of the same elements, carbon, hydrogen, sometimes oxygen, a few other elements, usually there's a variety of ways that those atoms can be put together to form different structures, much the same way that you can take the same set of Lego bricks and put together a variety of different structures, all using the same basic building blocks. And so when we talk about two or more substances that, if we were to describe them via their molecular formula, they're all exactly the same, but when we actually look at their structures we see that they're different. These are what we call isomers. And there are different types of isomers, some of which we'll look at right now and others of which we will not. Four main types of isomers that we have are structural isomers. These are the most basic kind that would be described by the definition that was just given. You have the same molecular formula for two different substances, but their structures are different. Positional isomers are ones in which it's simply the position of a given substituent is different. For instance, if you had 2-methylpentane versus 3-methylpentane. The only thing that's different is where that methyl substituent is positioned. Geometric isomers come into play when we talk about double bonds being present in a hydrocarbon structure, because the double bond prevents rotation around the bond axis. With an alkane, a single bond, you don't run into that kind of situation, that prohibition. You're able to rotate freely about that. And then finally, functional isomerism is where you have extra elements such as oxygen or nitrogen present, and how they are arranged in the structure, the functional group that they form or are a part of, is different from one molecular formula to another. The molecular formulas, when they're consolidated and condensed, are the same for two different substances, but if those particular elements form different functional groups, then that leads to a fourth type of isomerism. Again, the type that we're going to focus on right now, however, is structural isomerism. So two examples here. Isomers of the same substance. Now here you only see the carbon skeletons, but if you were to fill in the hydrogens and write their molecular formulas for both of these, you would see that the molecular formulas are C4H10. And so if we link those four carbons together in a straight line, a straight chain, we would get the butane structure. However, if we were to take one of those end carbons off, one of those terminal carbons, and stick it onto the center carbon of the remaining 3-carbon chain, thus creating a methyl substituent group, we would get 2-methylpropane. Now if you apply hydrogens to each of the carbons and count, you see that you get the same exact number of hydrogens as you did in butane. And so the molecular formula is once again C4H10, but now we have a different structure to those atoms being put together. And so if you were asked to determine the isomers of a particular compound, start with that compound and draw its structure, but then systematically take one carbon off the parent chain and put it in every single possible location that you could, and then name that structure. And go through and keep doing that, keep moving that one carbon until you've exhausted all possibilities. And the way that you can tell whether you've got a unique, valid isomer structure or a duplicate is to actually name the structure. If you name a structure and it's got the same name as one that you've already done, even though it may look differently, if it's named the same way, it's a duplicate and it doesn't count as an isomer. You can only use a name once. Once you've exhausted all the possibilities with that parent chain, then pluck a second carbon off of the end, if you can, if the parent chain is long enough. And then work with those two carbons, whether you work with them as methyl groups, methyl substituents, or if the parent chain is long enough and you're able to use them as an ethyl substituent, then look for all the different possible isomers that you could have in that configuration. And in going that route, you can systematically, figure out how many isomers there are, what their names are, and you can make sure that you haven't missed any along the way. It's a much, much more efficient manner of determining isomers than simply trial and error method of attempting to determine those isomers.